Thanks for having me here today. So my name's Rob. I'm the Catalyst Technologies Lifecycle Assessment Lead in Johnson Matthey. So Johnson Matthey is made up of 4 different business units at the moment. There's Catalyst Technologies, which, as you may observe, makes catalysts. There's also Hydrogen Technologies. There's PGMS, which is Platinum Group Metal Services, and there's Clean Air as well. So Johnson Matthey Catalyst Technologies, it has products and services that span syngas, which is short for synthesis gas, petrochemicals, oleochemicals, and biochemicals, as well as refining. So the syngas portion from the left-hand side of this slide, you can see that we've separated this out into feedstocks, building blocks, and intermediates. We are a chemical company at heart, so I know this is very specific towards construction, but a lot of the chemicals that we make end up being building blocks and intermediates for things that are used in construction, such as adhesives and things like that. Looking at the feedstocks, typically a lot of the feedstocks that we have to work with are things like natural gas and coal. We also look at petroleum, natural gas, liquids, as well as biomass and natural oils, which is becoming more and more prevalent, as well as crude oil. You can see here that there's a teal coloring. Anything with teal shows that we produce catalysts and sell those into those markets. Anything with a slight pink tinge shows that we develop technologies and model these technologies, effectively manufacturing plants, and sell that to customers who then build those plants and manufacture these chemicals. So we don't actually produce formaldehyde ourselves, but we sell the technology to do so. Several of these areas have a high priority for life cycle assessment metrics to prove that they can make a meaningful reduction to environmental impacts. So in the product side of things, like I was mentioning, we have catalysts and guards. For those that don't know what a catalyst is, they effectively let us allow reaction pathways to occur that may not otherwise occur, or they make them have a higher yield, so they make the processes more effective. So to prevent things from being damaged, obviously, it's very important. But yeah, so the guards themselves, they sit in front of the catalyst, so they absorb anything that might be harmful, and they have to get replaced more often. For licensing technologies, there's a lot of interest in bio-based feedstocks nowadays, so things like using woody biomass, secondary biomass, lignocellulosic biomass, e-fuels, so looking at things like converting CO2 and electrolytic hydrogen directly into another chemical like methane for ES&G, or for something like methanol, e-methanol. And then also the fossil technologies, the conventional ones that you may know of, using things like natural gas in steam methane reforming to produce hydrogen. We can still look at ways to improve the fossil fuel technologies, but there is a limit on what you can do because they inherently have a high carbon footprint. And then within research and development, looking at different materials for the catalyst, so looking at alternatives instead of using, say, platinum group metals or using base metals, what can you use instead? And also the preparation methods, so using alternative solvents and things like that. So I'm going to talk to you about 2 different case studies. They're based on 2 ISO 14040 reports that we've done, and anyone who's done an ISO report knows that they are quite a lot of effort to do, especially when you get them third-party reviewed. This one in particular is looking at how we had a reduction in nickel metal used with the Catalco 25, 55, and 57 series catalysts, and this effectively caused a reduction in the global warming potential 100. The nickel catalyst you can see is on the left-hand side there. There's varying different shapes and sizes, but it's composed of nickel metal impregnated on a calcium alumina support. So these products essentially allow the steam reforming reaction to generate hydrogen from methane at a high yield and more selective. The proprietary eggshell design has an optimal metal placement, which reduces the amount of nickel metal required, but it still maintains the same efficacy by enhancing active metal site availability. So as you can imagine, if you just have a pellet, you're trying to impregnate nickel onto it, that ends up going into the pellet as well, but the surface area, the outside of the catalyst, is what's interacting with the methane. So if you can prevent having to put metal where it's not going to get used, you can essentially have the same efficacy, but with less nickel. So it's cheaper for us. It also allows us to then have the same efficacy for the catalyst as well. So the customer really likes that. And so we ended up doing an ISO third-party report. So our commitment to the customer success and sustainability has led to this development of the 57.6 instead of the 57.4. It achieves up to a 30% reduction in carbon footprint compared to the 57.4 series, and that's lowering both Scope 1 and Scope 3 emissions. And it's been proven in some of the world's largest hydrogen plants. It has a proprietary eggshell design, as I mentioned, and that optimal metal placement. The design helps lower the catalyst carbon footprint and reduce critical raw material usage, and as well as that unwanted byproduct generation during the process. And we're constantly adopting Catalca 57.6 in sales to try and reduce the product CO2 emissions by over about 10% and reduce the critical raw material use and byproduct generation by over 30% over the next 10 years, so as our sales continue to grow as well. So a few learnings from doing that ISO report and working with engineers, working with people on the plants who manufacture these catalysts, working with also the R&D, IP, lawyers, lots of different areas. Getting sign-off from primary data from the plant experts is harder than it looks sometimes, so it's important to get all these different stakeholders on side. Getting sign-off from technical experts about the IP and trade secrets, especially before you know you're going to release this information online, you can end up giving away effectively the special sauce sometimes if you're not careful, so making sure that everyone's happy that that's not happening is really important. The commercial naming of the products, so I've called it in here 57.6, but other customers may know them as different names, so it can get very confusing if you're talking about one product in a call with them and they are not understanding what you're talking about, and it can just help by having the right naming. Data managers and links to source data, so anyone who's done an LCA knows that making sure that you've got the right data, but also you don't have to rely on someone sending you an Excel via an email every time you need some updates is really useful. And then understanding of LCA impacts and how to implement those changes. So we looked at carbon footprint here. We also did all the other impacts that we could. So we looked at water use via AWARE, for example. And just because you're reducing carbon footprint doesn't also necessarily mean that you're reducing your other impacts as well. So it's really important to make sure that by making a change, you're not just inadvertently increasing an impact somewhere else as well. So the second case study I'd like to talk about is a technology case study, and it's a comparison of our methanol technologies against a fossil fuel benchmark. So you can see here, I've listed a table with the methanol technologies we have, although it looks a bit skewed here. But we've got the Emerald technology on the left, and that's e-methanol, so that's an e-fuel, as we were talking about. We've got biomass to methanol technology, which is biomethanol. We also then have the balance technology, precision, and switch technologies, all of which use natural gas as a feedstock. And in our study, for Emerald particularly, we used a point source of CO2 from biomethanol production, so that CO2 is biogenic. We also then used hydrogen from electrolysis, which was produced using a grid renewable energy mix from the EU27. For biomass to methanol, we used a residual wood from primary forest industry, as well as the same renewable electricity process. And then for natural gas, we use an EU market average and an EU grid mix for the electricity. Methanol is a key foundation chemical that is conventionally made from fossil-based syngas, that's natural gas or coal. The balance, which is a steam methane reformer plus an autothermal reformer, and then precision and switch. Switch specifically uses a technology which allows us to switch in, instead of using natural gas for heating, it allows us to use electricity. Thereby you can supplement with renewable electricity and lower the carbon footprint, for example. These all use natural gas and our proprietary gasification designs. And as I said, Emerald uses CO2 and hydrogen streams, and biomethanol uses syngas via biomass gasification. We use the CO2 uptake metric, including uptake metric, to show how the Global Warming Potential 100 is affected by biomass feedstocks from cradle to gate. We had a bit of a decision point to make with this, because we did both the Global Warming Potential 100 as well as the Global Warming Potential 100 including CO2 uptake. At the time, the IPCC, I don't think, had the methodology which included CO2 uptake, but SumoPro handily did have that as an additional. So we looked at the difference here, and we found that because we were using biomass feedstocks, if you look at the two columns on the right of each graph, on the left side, sorry, you can see that the biomethanol and the Emerald, they have a negative carbon footprint, and that always should raise alarm bells when people say you have a negative carbon footprint. But in this case, because we're at cradle to gate, what this effectively is saying is that because we've used a biomass-based CO2, or biomass, that carbon is temporarily sequestered, so that's why it's negative. If you were to, say, burn methanol in a marine engine, which is becoming more and more a popular potential choice of marine fuel, obviously the combustion emissions would even that out, and it would become positive again to some degree. So as we can see from these graphs, the biomethanol has the lowest Global Warming Potential 100. Most of the impact is associated with the feedstock. Emerald technology has a less negative GWP 100 than biomethanol, and the hotspot is actually due to using EU27 renewable electricity. If you use a lower carbon footprint electricity, you'll have a more negative carbon footprint. And then switch technology has the lowest Global Warming Potential 100 of the natural gas processes, and that's because, as I said before, you can substitute heating with natural gas with heating with renewable electricity instead. The SMR benchmark is roughly the same as the balance and precision technologies. We took that data from the literature, and we had some good correspondence with the University of Leeds about that, just to make sure we knew what we were doing with that data. Some lessons learned here, and I think this is one of my favorite projects we've worked on because we got to work directly with engineers as well, who, I don't know if anyone knows any chemical process engineers, but they're usually very detailed and they can pick holes in almost anything very easily, so it helps us effectively make our models much more robust. So for example, we used to have a lot of questions when we presented this to them, showing things like the sensitivity analysis of key hotspots can enable a more informed discussion and balanced view. So they'd ask questions like, why are the values for e-methanol higher than other reported values in the literature, i.e. why is ours looking worse in your analysis than others, for example? And then we talked about the E27 grid mix, that helped, and we showed them the sensitivity analysis with different electricity carbon footprints. Why are some of the values negative, talking about sequestration. Have you included is one of my favorite starting points to a question, so always asking about what they've included in the system boundaries and things like that. And then what happens if you is probably the most important part when they start asking that, because that means they're thinking about modifying their flow sheets for you, which is a really cool thing to happen because they're considering that not only is your analysis robust enough for them to take it seriously, but also that they're willing to try and modify things to see if they can get a lower impact on the environment. So yeah, that's one of the best questions you can hear, or one of the hardest to ask, to be honest, answer as well. So as Catalyst Technologies continues, and you'll see I've said Catalyst Technologies specifically because this business unit actually is currently undergoing acquisition from Honeywell. We are going to try and aid with informed decision making when deploying sustainable technologies. So we talked about products here, so looking at the catalysts again. How can we do more metal thrifting but maintain the efficacy of the catalysts? Are there any alternative raw materials that we can use instead of base metals and platinum group metals? For licensing technologies, looking a lot at the upstream processing, so we don't currently have a biomass gasification technology, but we had to use a model for one. So understanding and partnering or looking at partnerships with companies that do that, and then we can get better primary data and model it better. Co-product use and credit. If there's in a lot of these processes, we generate a lot of excess heat due to the exothermic reactions we have, so that can be turned into steam, but it has to be used, right? We can't just say, oh, we make a load of steam, great, we're going to get a minus on our carbon footprint, right? We actually have to consider ways where that can work. If you have a standalone plant in the middle of nowhere, there's no one to send it to, so you're just venting it to the atmosphere. That's not going to work, I'm afraid. And then, as well as that, other things like how we look at counterfactuals, right? So if you're using a feedstock like municipal solid waste, if you're taking that municipal solid waste away from somewhere that's incinerating it for electricity, how are they going to get electricity instead, right? Those kind of things, all those assumptions. And then looking at a research and development angle, alternative chemical pathways. I know that a lot of chemical companies have done their processes for a long time, decades, maybe even over a century, but can we do it in a different way that actually might have a lower carbon impact and also lower environmental impact as well? So in conclusion, Catalyst Technologies has completed these ISO third-party reviewed reports for its major methanol technologies and steam reforming catalysts. Got some few key lessons here. Involvement of the right stakeholders from the start. It reduces delays during the report writing as well as the modeling, and it improves data quality. But it requires organizational upskilling, and it also inclusion in their project management workflows. Showing sensitivity analysis of key hotspots can enable a more informed decision and balanced view that can overwhelm and cause confusion. CT in the future will focus on continuing to improve assumptions and data pipelines, things like how we calculate things from stoichiometry, for example, for emissions and things like that. Focusing on digital material and product passports, although catalysts and our technologies, specifically our catalysts and products, probably won't be in the limelight for a little while with those. I think it's good to get ahead of that. And completing LCAs for the remainder of our sustainable solutions as well. That's a bonus slide. And that's everything from me. Thank you.